one do you like? That one? Okay, alright. I mean, it's your choice. My cat chose this color, so. Oh God, I didn't say anything. I recorded this whole thing twice and I didn't say anything. So here we go. The third take on the third chapter. It talks a little bit about variables and mutability, and that led me to a question here, which is, I assume that shadowing was kind of like the less than common used option, and that making a variable mutable was more of like the standard way of saying, yep, I'm intending to change this. And that was probably incorrect, because there's something that mutating variables can't do, which is change type, which is kind of the whole point of shadowing, which makes the shadowing like more useful. And what I thought was interesting about it is when we're talking about redefining these guys with shadowing, I want to know if I can keep the same type, because if this is possible, then what would be the value of having mutating variables at all? You would just be redefining them each time. Perhaps that's a performance issue, but I can't imagine for something as simple as like a counter you're really going to see much of anything at all. And to kind of describe that in a way that maybe is a little bit more visually understood, if we have our stack, which is just a bunch of spots we can put things, and we put in some sort of value in one of those spots, and we'll call it X in this case, and we give that value 5, and then we shadow it, what we're saying is, get rid of that, we don't want that anymore. Put a new value, and we're going to reference that later as X, but that new value is going to be something else. We'll call it 7. And so I could presumably do the same thing with both of these let calls here, where they're both 5, and functionally that'd be like, put the 5 in this piece here, and then, oh wait, no, we're shadowing it, get rid of this thing, throw it away, we now want a new one, oh, give that the value 5, and then we're going to give it the value of X, or reference it in this way with X. And if that's possible, you can imagine how it's maybe more expensive to do than updating something. So same example, we have a bunch of places where we can put things inside of the stack, and we say, hey, X is equal to 5, and then it's a mutable variable, and we say, hey, now X is equal to 7. So we say, okay, instead of getting rid of this, finding another spot, putting that value in, we simply say, change this value to 7. And that way we don't actually have to go back in and say, now X references this particular box here. It's just now we know it's 7. So it seems to me that this is nice in the sense that we get to keep the same variable name, but it's more expensive to do, and that it's more powerful than I had initially thought. I had assumed the mutating variables was the more standard, powerful way to do things. It looks like shadowing is the way to do that. I also was so excited that I skipped over constants. So constants are like variables, except they don't vary. And they also, in this case, you might be saying, well, if all variables unless defined are non-mutating, why would we have any distinction between a constant and a non-mutating variable? And that's a good question. It has to do with the way we scope things, and we can have constants be in the global space, which I guess implies that we can't have variables in the global space. I'll have to check that one out. We also have to worry about two things syntactically with constants. One is that we always define the type. You can't just be like constant x equals 5. It's like constant x of a unsigned 32-bit integer equals 5, and then it's okay. More than just that, you can't say constant unsigned 32-bit integer x equals the result of this function that will return that, because it goes, nope, that's not a constant. That function can return two different values. We want them to be very statically defined. And so they particularly say that it can only be set to a constant expression, and it talks about expressions and statements immediately after it talks about these types. But we're going to keep going a little bit into these guys. Oh, wow, it doesn't show it. Okay, so we know that there's a potential max size for, let's say, an 8-bit signed integer. If we go beyond that, what happens? Well,
It depends on how your Rust is compiled. If it's compiled as a build, then it will panic and say, yo, you overflowed this integer. But on a release, it doesn't do that. I'm assuming that's for performance reasons, but it also means that we need to be extra careful when we're writing tests so that we know to check this while we are working in our builds and where it will panic and let us know something's wrong, because in release that won't happen. It'll just have unforeseen consequences and have problems. What's nice about this is it shows that if you're writing some sort of algorithm that expects this underflow or overflow behavior for it to work, then you should use this wrapping type inside the standard library. And if you're not intending that, you should consider any sort of overflow as an error, which just sets a precedent that if you're the type of person to be writing these algorithms, that this is something you should know and that it's available to you in Rust, which tells me that they thought about it. The other thing that is maybe potentially interesting if you're coming from some languages that worked in the past, because most of the time that they're using a standard that, ties a integer value to a character value, and that commonly in the old days was done with ASCII, and that's no longer a thing. So, we've grown past ASCII. We humans have always needed characters beyond what's available in ASCII. So we know that in this case we have Unicode, which is more universal, it has more flexibility, and so characters in Rust are Unicode by default, and I think that's cool. As the encompassing blob of all of our scalar types, we have a data type called the compound type, and they give us some examples of them, and obviously you should be reading this for yourself, but in this case we have tuples, we have arrays, and we have vectors, and it talks about vectors in here, and it says I'll go into them in more detail, but it's important to know that because vectors are what most of us know as arrays in higher level languages, and that's cool. So a tuple is basically a thing that contains a specified, predefined, this sized thing and contain any number of those types. So in this case, we have I32, but we could have string, we have floating point 64, and all these are available, and they're addressable by either unpacking it like this, or you can reference them by providing a dot and then whatever the index of it is. So you're getting the 0th element of this X thing. So you're getting the I32-bit value 500, which would tell us that this is going to return 500 there. Cool. Then you have arrays, which are similar to tuples, except they can't have multiple different types. And they're useful because tuples can't change. You can't say this particular value in the tuple is now this other particular value. They're just what they are when they're defined. Arrays are meant to move stuff around, change values inside of things, and you can reference them very quickly by their particular index. And that's cool. And you might be like, hey, I'm making a thing and I don't know the size of it to begin with, or I don't know how big it needs to be and all this stuff. And that's why a vector comes into play. And that's pretty much all we need to know for right now, but they work very similar as to arrays because they can only carry one particular type. I included this here because I want to know for myself, but you know that an array can only have 5 things in it, so the computer can say, here's a chunk of memory that contains what's necessary to store 5 of these things, and that's useful and efficient. But when we're talking about a vector, it doesn't know how to size that out or how to reference things inside of it, so there might be overhead associated with that, and that's perfectly acceptable. But I don't know when we say, okay, I've deleted something from this vector. Does it just shrink automatically, and does it do that computation when that happens, or does it wait some period of time when it believes it to be most efficient? I have no idea. I'd like to learn about that, so I made a sticky for me. One other thing, I put it in pink because it was like subtle and I wanted to draw attention to it, is when you're defining these tuples, you use the parentheses as you define the actual types of what's inside of it. And for arrays, you use the square brackets because that's what the array type is. That's definitely going to trip me up. So when we're going through our code, we don't necessarily just want to go from the top to the bottom. So we want to have ways we can like reference one thing over and over, or like have something loop for some number of times. skip this thing when some certain criteria apply, and that's all control flow. The first thing it talks about is functions. If you're like me, you're familiar with them, but I wanted to write something specifically for how Rust handles something like polymorphism, because in this particular example, it says we have to declare the type of a function. And so I don't know if I make this another function, if I made a second another function, which had different types, how that'd be handled. It makes sense if I'm calling it, because I know the types now, which one I would want to execute, but I don't know if it's going to be upset because I have two functions called another function. I'm going to skip a little bit of this piece here because it talked about statements and expressions and how they're different and why that's important. And I think that that's probably important, but I didn't really have the context as to where it'd be used until reading this later part. So I'm going to start there and kind of work back. What I thought was interesting here is we're saying let this number equal the value of this potential condition and then what is potentially returned in this expression. So that feels a little bit weird, but it doesn't seem super complicated when we're reading it, because we're saying let the value be dependent upon what this condition is, and then in this case we're considering what we want to return in that case. And what's subtle here is that we have this 5 and this 6, and they don't have semicolons after them, meaning that they're not statements, they're expressions. We're returning that value 5 to this little squiggly, and then therefore putting it into the value of number. That seems a little bit weird. And what I've seen a lot in the past is people will have like a thing called a return, which is like, now I know I'm exiting this thing at this place. And this to me makes sense now that I understand the prerequisite. Hey, having a semicolon means it's a statement, and not having that semicolon means it's implicitly returning that value. But it's subtle and it's likely to mess me up, and so maybe it's likely to mess you up. So when we talk about statements, we're specifically talking about things that either are just defining something and not returning something, or we're talking about expressions, which are things that return a value. So it gives this example of let x equal let y equal 6. Well, this part is perfectly fine because we're saying y equals that value of 6, but we're not returning the value of 6 in there. Other languages do allow you to do this, so you can say let x equal y equal 6, and that's perfectly valid. But this is a statement, it's not an expression, and so x needs a expression, a value to define itself, and we don't get anything returned back here, so it's a problem, and it gets upset. And I put this in pink here because it was subtle, and I wanted to draw attention to it, that the semicolon specifically says this particular thing is being returned. In this 5 function here, we do not have this semicolon here. So when we call 5, we can use that as an expression for something else. But if we had a semicolon here, 5 would do whatever, it'd perform whatever inside that function, but it would never return anything. And therefore this x value wouldn't be equal to anything because there's no return, and it would get upset. Another cute thing here was I highlighted let result equal loop whatever, meaning that when we have this break call here, it's actually returning the output of this expression and then defining result in that, which is not something I've seen. I've never seen like let x equal for this thing, right? It's a little bit different than the way I've seen stuff in the past, and that makes sense to me, but I wouldn't have known that that's a possibility. It lastly talks about for, and for's like a super common thing. You've probably seen it in a lot of different places in a lot of different ways. Essentially like for I equals 0, I less than 10, I plus plus, do the thing, and then you reference I because you know I is changing each time. And in this case, we have a for loop, but we're going to be defining a range. So we say for number in this range, and I'm going to cover up this reverse call. For number in that range, it's saying number is going to equal to 1, number is going to equal to 2, number is going to be equal to 3, and ranges are inclusive on the lower end and exclusive on the upper end. So this is just a range from 1 to 3. 4 doesn't actually get executed in here, and then we're done, which is cool. We don't have to say I equals some value, and this might not be super obvious, but that's useful because we can then talk about enumerating through things. So in this case, we have an array, and we don't have to define an index of that array and then use that index to point to something in the array. I can just simply say the element would be 10, the element would be 20, the element would be 30 as this for loop processes. What I am not sure about, and I'll need to do some check on specifically, is that elements inside this particular value might be modified. That's perfectly acceptable. But if we have some sort of thing we're iterating over that is not fixed in size, if we're going back to our vector from really early when we were talking about things somewhere here, if we're talking about our vector that can grow and shrink in size, if I'm in the middle of iterating through something and I delete something potentially later in this, does it get mad? Does it panic? I don't know if that's something that's going to be checked at compile time or panic at runtime, but I want to know if I have a vector and I'm moving through it and I delete something, will it be like, hey, you're modifying this thing I'm iterating over as I'm iterating over it. Stop, you're in unforeseen territory. I put a couple little stars as I've been going through for really, really short, quick notes that I thought were worth pointing out. So firstly, remainder here makes sense that they're calling this operator a remainder. In a lot of other computer science contexts, it's called modulo. It's on the screen. I looked it up after, but you'll hear mod. So in this case, people would often, as they're speaking this out, go 43 mod 5. And that's useful to know because if you're Googling something, you might have to search mod instead of remainder. This little spindly do has to do with compiled languages versus runtime languages. Correct me if I'm wrong in the comments. I don't know really what you'd call non-compiled languages. Anyway, we're talking about here, this another function gets called, and this another function is referred to further in the code down. And when I was using my little instruction pointer finger guy, this can be a problem in runtime languages because it says, okay, I'm executing main. Okay, I'm executing another function. I haven't seen another function. I don't know where this is. Panic. But when we're talking about a compiled language, it looks at all this code and then creates a compiled binary that your computer can then run. That compiled binary contains all this information. It writes it into a read-only part of that executable, and then when it says, oh, another function, I know where that is. I've already compiled this. It's here, and then executes. That's important to know because it's something that maybe I didn't recognize would be important for everybody, something that I have a tiny bit of experience with, and that might have tripped you up. The last little star guy that I have is related to truthiness. This was something that existed in languages I've used in the past. So truthiness would be like, if this array, you're saying if this array is empty or not. Or if I say if this number, I'm saying if this number is anything other than 0. Or if I say if this string, it's if this string is just empty, like I just quoted and there's nothing inside of it, or it contains some value. And that's not something that we get with Rust. It's saying if we care about determining some control flow based upon the value of a number, you just have to explicitly define it. It's not something that you just get for free. You can't just say if number, it'll be mad. Hello, desktop me here. Hopefully the hands weren't too boring. I certainly felt so by the time I got into the code. So let's talk through some stuff, see if we get some answers to the questions that I had brought up. Firstly, I was wondering if I can just shadow the same thing multiple times, what's the point? I essentially get the value of a immutable object, but I would have to change it each time. Yes? Question mark. So I came up with this example here where I say let x equal 5, and initially I didn't have this print line statement, so we can comment that out. And then I would just do another call immediately, let x equal 5, and then return it. And we'll just see, does this equal 5? So when we run this, we see that we get a, hey, you didn't use this variable. Was that intentional? Do you want that to be the case? So if I go back here and I add in my print statement again, I find that I don't get that particular error, which is interesting. So we can, I guess, always shadow variables
of themselves with their same values. There's no like check to ensure that that doesn't happen. But I'm assuming that this might be optimized out by the compiler. And to show, I guess, what happens here, I can always just remove all of these different lets. It'll still run just fine, except we get a bunch of different warnings. So if you were doing this, it's pretty clear from the compiler that you're wasting a lot of time and energy, and you could be doing things more cleanly. Okay, so for the second question, where we're asking whether or not we can do polymorphic function declarations, I have a function here called polymonomorphic, and we're going to see if we can add in this other guy down here after changing its parameters type. But just to show that it's working, I can call 21 and provide it the value 21, and when we run it, we get 21, and that's great. If we create a new polymorphic function with a different value, and I'm just going to save this, let's see which one it tries to pick. Looks like we got a compilation error though, and it's upset because like we had potentially thought, polymonomorphic can only be defined once within this namespace. So it doesn't look like you can do a standard walks like a duck, quacks like a duck polymorphic functions within Rust. So it's good to know that the compiler is going to catch that. Wow, the code changed between the last time you talked and now. What happened? Well, it turns out that I was learning, and now I have more context to tell you about. So I made this function called do the loop, de-loop, and pop, and I create a vector, and my intention is to go through this vector and remove things from it while I'm looping through it. That doesn't appear to be possible. So if you look on the left hand of my screen, we can see that we attempt to borrow a value here. And it's a problem because we've already used it in this for loop just to print out what's available to it. If I then comment this guy out and that for loop's the only thing using it, and I try to run this again, I can print out everything. And if I say, let's modify this in place, we find that I'm not allowed to. I'm borrowing it inside of this for loop even. So if I wanted to pop something from it, I could potentially say, hey, I'm borrowing this value, and then I'm trying to pop it, and it goes, whoa, 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 you're already borrowing it. You're now trying to mutate it. That's not allowed. So the compiler's mad there. And if I was to say, hey, let's borrow this and then print it, everything works as expected. But if I then try to remove anything here, it's going to be equally upset. I think that should be clear regardless of if the print line's at the end copying it. What I learned though is you can call clone on these, and what clone will do is make a different copy of that, a clone of that whatever you gave it, and it will then run, at least in this for loop, on whatever that cloned value is. So v's never really touched, and that means that I guess I should say not v's clone is never touched inside this for loop. So that means that as I'm stepping through v's clone, I'm popping everything inside of the original v, and then when I ask what's in it at the very end, I don't get anything. Now, this is not purely exhaustive, but I think it goes to show what my tools will be in the very near future as I'm working with Rust, that if I'm having issues with the borrow checker and I'm just trying to get something to work, I can try running stuff with clone, even though I know it's going to be non-performant, and then reassess at a later point when I have a better understanding of how the language works, where this clone might be removed and where I can better work with the borrow checker. And then the other thing that I think I learned here is that a lot of the errors I would have seen in other languages might in fact just be bucketed in this borrow checker. That sounds a little bit non-intuitive. The borrow checker's doing its job, but it's more or less informing me that I'm modifying something in a way that's not consistent or is likely to cause errors. And the first case where I found that was where I was saying, hey, I know that this causes errors in other languages if I'm changing the elements inside of a thing that I'm iterating over. Does that happen in Rust? And the answer is, well, as far as I can tell, you shouldn't do that. The borrow checker's there to specifically prevent that. So I'm going to be a little bit more understanding when I try to get these borrow error issues, because they're informing me that I'm doing something that's going to potentially cause unexpected behavior. And I know that if I'm doing something that's not performant to get around it, that I have room to improve to come back and fix this stuff up. It does make me wonder whether or not eventually I can essentially turn off the borrow checker to do some more complicated things. I know that people have mentioned stuff like unsafe with Rust, but I have not looked into it enough. So if you have more context as to this particular problem and how I could make Rust behave in an unsafe way, that'd be interesting to me. Sweet. So that should wrap up this chapter. I appreciate you guys listening to me ramble for a little bit. And hopefully if you learned something that is new or exciting or worthwhile and you wanted to share related to this episode, or as you went through this, you saw something that you need clarification on, or something that I struggled with that you just made sense to you, let me know in the comments of this video or reach out to me over email, and I'll make sure to include that in the next chapter. The types specifically, or I guess I should say the data types according to this book, are defined as either being scalar or being compound. And I don't really know what the word scalar means. Hey Siri, what does scalar mean?
As a noun, it means a scalar quantity.
Okay, great. So scalars are of a scalar quantity.